Hello friends. Welcome back to my channel. Today we are here with brand new video. In this video I'm going to express about stresses on ships. A ship is subjected to various stresses during various weather conditions, both from static and dynamic forces. These dynamic stresses experienced by the ship when at sea may conveniently be considered separately as longitudinal stresses, transverse stresses, and local stresses. Dynamic forces are generated by the ship's motion in waves and wind, as well as by the operation of machinery. Longitudinal stresses are bending like shagging and hogging, transverse stresses are racking and torsion, and local stresses can be listed as panting and pounding. If a homogeneous body of uniform cross-section and weight is floating in still water, at any section the weight and buoyancy forces are equal and opposite. Therefore, there is no resultant force at a section, and the body will not be stressed or deformed. A ship floating in still water has an unevenly distributed weight owing to both cargo distribution and structural distribution. The buoyancy distribution is also non-uniform since the underwater sectional area is not constant along the length. Total weight and total buoyancy are of course balanced, but at each section there will be a resultant force or load, either an excess of buoyancy or excess of load. Since the vessel remains intact, there are vertical upward and downward forces tending to distort the vessel, which are referred to as vertical shearing forces, since they tend to shear the vertical material in the hull. The ship shown in figure will be loaded in a similar manner to the beam shown below it, and will tend to bend in a similar manner owing to the variation in vertical loading. It can be seen that the upper fibers of the beam will be in tension, as will the material forming the deck of the ship with this loading. Conversely, the lower fibers of the beam, and likewise the material forming the bottom of the ship, will be in compression. A vessel bending in this manner is said to be hogging, and if it takes up the reverse form with excess weight amidships is said to be sagging. When sagging, the deck will be in compression and the bottom shell in tension. Lying in still water, the vessel is subjected to bending moments, either hogging and sagging depending on the relative weight and buoyancy forces, and it will also be subjected to vertical shear forces. When a ship is in a seaway, the waves with their troughs and crests produce a greater variation in the buoyant forces and therefore can increase the bending moment, vertical shear force, and stresses. Classically, the extreme effects can be illustrated with a vessel balanced on a wave of length equal to that of the ship. If the crest of the wave is amidships, the buoyancy forces will tend to hog the vessel. If the trough is amidships, the buoyancy forces will tend to sag the ship. In a seaway, the overall effect is an increase of bending moment from that in still water when the greater buoyancy variation is taken into account. When the vessel hogs and sags in still water and at sea, shear forces similar to the vertical shear forces will be present in the longitudinal plane. Vertical and longitudinal shear stresses are complementary and exist in conjunction with a change of bending moment between adjacent sections of the hull girder. The magnitude of the longitudinal shear force is greatest at the neutral axis and decreases towards the top and bottom of the girder. It was seen earlier that the ship bends like a beam, and in fact the hull can be considered as a box-shaped girder for which the position of the neutral axis and second moment of area may be calculated. The deck and bottom shell form the flanges of the hull girder, and are far more important to longitudinal strength than the sides that form the web of the girder and carry the shear forces. The box-shaped hull girder and a conventional eye girder are compared in figure. In a ship, the neutral axis is generally nearer the bottom, since the bottom shell will be heavier than the deck, having to resist water pressure as well as the bending stresses. In calculating the second moment of an area of the cross-section, all longitudinal material is of greatest importance, and the further the material is from the neutral axis, the greater will be its second moment of area about the neutral axis. However, at greater distances from the neutral axis, the sectional modulus will be reduced and correspondingly higher stress may occur in extreme hull girder plates such as the deck stringer, shear strake, and bilge. These strakes of plating are generally heavier than other plating. Bending stresses are greater over the middle portion of the length, and it is owing to this variation that Lloyds give maximum scantlings over 40% of the length amidships. Other scantlings may taper towards the ends of the ship, apart from locally highly stressed regions where other forms of loading are encountered. When a ship experiences transverse forces, these tend to change the shape of the vessel's cross-sections and thereby introduce transverse stresses. These forces may be produced by hydrostatic loads and impact of seas or cargo and structural weights, both directly and as the result of reactions due to change of ship motion. When a ship is rolling, the deck tends to move laterally relative to the bottom structure, and the shell on one side to move vertically relative to the other side. This type of deformation is referred to as racking. Transverse bulkheads primarily resist such transverse deformation, the side frame's contribution being insignificant provided the transverse bulkheads are at their usual regular spacings. Where transverse bulkheads are widely spaced, deep web frames and beams may be introduced to compensate. When any body is subject to a twisting moment, which is commonly referred to as torque, that body is said to be in torsion. A ship heading obliquely to a wave will be subjected to righting moments of opposite direction at its ends, twisting the hull and putting it in torsion. In most ships, these torsional moments and stresses are negligible, but in ships with extremely wide and long deck openings they are significant. A particular example is the larger container ship, where at the topsides a heavy torsion box girder structure, including the upper deck, is provided to accommodate the torsional stresses. Panting refers to a tendency for the shell plating to work in and out in a bellows-like fashion, and is caused by the fluctuating pressures on the hull at the ends when the ship is amongst waves. These forces are most severe when the vessel is running into waves and is pitching heavily, the large pressures occurring over a short time cycle. Severe local stresses occur in way of the bottom shell and framing forward when a vessel is driven into head seas. These pounding stresses, as they are known, are likely to be most severe in a lightly ballasted condition, and occur over an area of the bottom shell aft of the collision bulkhead. Ship structural members are often subjected to high stresses in localized areas, and great care is required to ensure that these areas are correctly designed. This is particularly the case where various load-carrying members of the ship intersect, examples being where longitudinals meet at transverse bulkheads and at intersections of longitudinal and transverse bulkheads. Another highly stressed area occurs where there is a discontinuity of the hull girder at ends of deckhouse structures, also at hatch and other opening corners, and where there are sudden breaks in the bulwarks. If the minimum designed draft forward in any ballast or part-loaded condition is less than 4.5% of the ship's length, then the bottom structure for 30% of the ship's length forward in seagoing ships exceeding 65 m in length is to be additionally strengthened for pounding. Where the double bottom is transversely framed, solid plate floors are fitted at every frame space in the pounding region. Intercostal side girders are fitted at a maximum spacing of 3 times the transverse floor spacing, and half-height intercostal side girders are provided midway between the full-height side girders. If the double bottom is longitudinally framed in the pounding region, where the minimum designed draft forward may be less than 4% of the ship's length, solid plate floors are fitted at alternate frame spaces, and intercostal side girders fitted at a maximum spacing of 3 times the transverse floor spacing. Where the minimum designed draft forward may be more than 4% but less than 4.5% of the ship's length, solid plate floors may be fitted at every third frame space, and intercostal side girders may have a maximum spacing of 4 times the transverse floor spacing. As longitudinals are stiffening the bottom shell longitudinally, it should be noted that fewer side girders need be provided than where the bottom is transversely framed to resist distortion of the bottom with the slamming forces experienced. Where the ballast draft forward is less than 1% of the ship's length, the additional strengthening of the pounding region is given special consideration. Greater slamming forces are experienced when the ship is in the lighter ballast condition and is long and slender, by reason of the increased submersion of the bow in heavy weather with impact also on the bow flare. Additional stiffening is provided in the four-peak structure, the transverse side framing being supported by any or a combination of the following arrangements. 1. Side stringers spaced vertically about 2 m apart and supported by struts or beams fitted at alternate frames. These panting beams are connected to the frames by brackets and if long may be supported at the ship centerline by a partial wash bulkhead. Intermediate frames are bracketed to the stringer. 2. Side stringers spaced vertically about 2 m apart and supported by web frames. 3. Perforated flats spaced not more than 2.5 m apart. The area of perforations is not less than 10% of the total area of the flat. Aft of the forepeak in the lower hold or deep tank spaces, panting stringers are fitted in line with each stringer or perforated flat in the forepeak, extending back over 15% of the ship length from forward. These stringers may be omitted if the shell plating thickness is increased by 15% for vessels of 150 m length or less, decreasing linearly to a 5% increase for vessels of 215 m length or more. However, where the unsupported length of the main frames exceeds 9 m, panting stringers in line with alternate stringers or flats in the forepeak are to be fitted over 20% of the ship's length from forward, whether the shell thickness is increased or not. Stringers usually take the form of a web plate with flat-facing bar. In tween deck spaces in the forward 15% of the ship's length, intermediate panting stringers are fitted where the unsupported length of tween frame exceeds 2.6 m in lower tween decks or 3 m in upper tween decks. Alternatively, the shell thickness may be increased as above. In the aft peak space and in deep tween decks above the aft peak, similar panting arrangements are required for transverse framing, except that the vertical spacing of panting stringers may be up to 2.5 m apart. If the forepeak has longitudinal framing and the depth of tank exceeds 10 m, the transverse webs supporting the longitudinals are to be supported by perforated flats or an arrangement of transverse struts or beams. So my friends, thanks for watching and please subscribe and share it. See you in next video.